Last speaker of the day is Konrad from University of Bristol.
Great, thanks very much. Thanks for inviting me and thanks for still being here. So this talk is about streaming algorithms, communication complexity, and the maximum matching problem. In particular, we'll talk about how streaming algorithms and communication complexity are related, and this will be illustrated on the example of maximum matching. So streaming algorithms, we'll see them in more detail in a minute, but essentially these are algorithms that have linear access to the input data, where essentially they do passes over the data sequentially in that sense. So this is sort of the one world we're going to look at, and the other world is the world of communication complexity. So in this setting, what we often look at is we have two parties that each hold a portion of the input, they communicate with each other and solve some common problem. And well, these models are connected. We know they're very well since quite a long time that they are connected, but they're connected and allow us to, so we can use communication complexity to prove space lower bounds for streaming algorithms. And how this works is sort of the objective of this talk. We're going to explore this a little bit more. So the outline is going to be the following. I talk first, introduce what sort of streaming in graphs looks like. Then I talk about communication complexity, the framework that we have, the connection between these two models, and then ultimately how this connection is leveraged to get space low bounds for matchings. I'll talk a little bit about independent sets as well, because this fits very nice in the picture into the story of the talk as well, towards the end. Good. Okay, so in the graph streaming world, so the streaming algorithms for graph problems have been considered since quite a while already, with the first works more than 25 years ago. The setting is as follows. So we see basically an algorithm sees a sequence of edges of an input graph, and these edges, they arrive in arbitrary order. So here we have a very short stream, 4 edges, and they make up a graph. We will generally measure the length or the complexity of our algorithms in terms of the number of vertices that we have. So here we have 4 vertices, so this would be the measure of complexity. Now, generally, we know that such a stream can be of length at most n square. We have at most n square edges in the graph, so the stream length is at most n square that we deal with. Now, what is the objective? Well, we want to design algorithms that go over this stream, hopefully only once, maybe a few times sequentially. But most importantly, they use as little space as possible. Space should be, of course, smaller than the number of edges. Otherwise, we could just store all the edges and we would hold those in memory and we could just operate sort of in an offline fashion on these edges. So the space should be certainly little over n square. It should be less than n in general. Good. Now, we're going to look we're going to study the maximum matching problem in this setting. So what is this? Here we have a graph. The red edges, they form a matching. They're basically a subset of edges that are vertex disjoint. And we say that this is, for example, a maximum matching. A maximum matching is one of largest possible size in the graph. So this is a maximum matching here in this case. The general problem we have is we want to compute an approximation to maximum matching, meaning that we compute a matching that's as large as possible, basically, measured by an approximation factor alpha that's here smaller equal to 1. So we want to compute a matching M such that its size is at least some alpha times the size of the largest possible matching of a maximum matching. So this is the problem we want to study. Good. So what's the most natural way of doing this? There's a very easy, simple baseline algorithm that we can consider. And this baseline algorithm is the greedy matching algorithm. So let's start with an empty matching. So we start with an empty set M. Just go through the set of edges that we have in the graph in any order. So this maps nicely to the streaming setting when we sort of receive or see a sequence of the edges of the graph in any order. We insert the current edge that we see into the matching, well, if it is possible, if the two endpoints are not yet blocked. So we just greedily add whatever there is in the input stream to our current matching. So this gives us a very nice baseline algorithm. Now, using this algorithm, so we observe 2 things. First of all, the approximation factor. So if you just do that, you greedily add edges to your graph, we have an unweighted graph, there are no weights involved, then the matching is actually not too bad. It will always be at least half the size of an optimal matching. So the approximation factor of the greedy algorithm is 1/2, which is great. We also see that the algorithm actually doesn't store that much information. It only stores the edges that we retain in our matching. So it doesn't have to store many additional edges, not much else apart from the matching. So the space of the algorithm is basically the space of the matching, just to write it down, which can be n log n to write it down. So we see this is, first of all, we express the space in terms of n, the number of vertices of the graph. For dense graphs, this is going to be sublinear. Here's a worst case example, which is quite nice. If greedy picked sort of the edge in the middle, it blocks these two outside optimal edges. So we might lose a factor of 2 basically in that sense. So we have a baseline algorithm for computing matchings in the streaming setting in a single pass. It gives us a 1/2 approximation. It uses the space n log n. This is often referred to as a semi-streaming space regime. N log n, n poly log n is what we typically want to sort of spend in terms of space for our algorithms. Okay. Good. Yeah, let's move on to the communication complexity setting. So it's a bit of a different world. So the way it looks like is we have, in the easiest setting with 2 parties, we have Alice and Bob. Alice and Bob hold the input to our problem. Alice holds the portion X, Bob holds the portion Y. Now, Alice and Bob, they exchange messages and to solve whatever problem is, we want to solve. Now, of course, Alice could just send X to Bob, then Bob has full knowledge, but that's not what we want. We want Alice and Bob to minimize communication. So the goal is really the minimum number of bits that need to be exchanged in any protocol involve whatever problem we have. That's sort of the goal, minimize communication in this setting. The setting also allows for randomized protocols. So we generally assume that a randomized protocol, Alice and Bob have access to sort of shared randomness, to a sequence of shared random bits as well. So this can help for many problems. We will also look at sort of 2 particular settings of communication complexity that are particularly relevant to streaming. So there's the one-way communication setting. So in this setting, again, it's the same setup. We've got Alice and Bob. But now communication is quite restricted, so we can't sort of freely communicate between Alice and Bob. We allow only Alice to send a single message to Bob, and Bob immediately has to output the result. That's quite a restricted setting. It's much harder to deal with because Alice doesn't know anything about Bob's input, just has to send a message based on Alice's input, and hopefully Alice sent the right information for Bob to solve the problem using input Y and the message itself. So that's the one-way communication setting that we'll also look at. And this can now be extended, this setting, and to a k-round communication setting, where essentially the communication is Alice to Bob, back to Alice, to Bob, back to Alice. And this can go on for, say, k rounds until Bob outputs the result. So this is what we would understand with the sort of k-round communication here. Good. Okay, but that's quite abstract, so let's look at an example. So the example that will be relevant for us now is the index problem. It's a quite well-known problem in communication complexity, and it's extremely powerful for us to prove low bounds for streaming. So in this problem, so let's look at it in more detail. Alice holds an n-bit string, so it's just a bit string of length n. Bob holds an index j, which is an integer from 1 to n. And the goal for Bob is to output the jth bit of x. So we need to know what the bit that's located at the jth position of x. And yeah, Alice doesn't know j, Bob doesn't know x. So certainly this is not so easy to solve. So the question is, in the one-way communication setting, Alice now looks at the input x, sends a single message to Bob. What should Alice send to Bob to solve this problem? And it turns out this index problem is a bit of a barrier problem. There is just no good protocol. So for this problem, we know that even if we have access to randomization, there's really not much Alice can do. If Alice doesn't know the index j, all bits look sort of the same. Alice just has to send everything to Bob to solve this problem. So the communication complexity of this problem is indeed omega of n. So there's no trickery possible for this specific problem. Good. So keep this in mind. So we'll come back to this problem a little bit later. But there is something quite interesting if we look at the index problem, but now we allow for unbounded rounds communication. So suppose Alice and Bob can communicate freely now with each other. So what could we do for the index problem in this case? Well, surely we can do better because, I mean, there's the trivial protocol. If Bob just sends the index to Alice, the index only requires log n bits. Alice knows exactly the answer. Alice just can look at sort of xj, knows the answer to the problem. So communication can be, quite small. We don't need many bits to solve the problem. But there's also an interesting trade-off possible, and let's look at this trade-off here. Suppose we look at a protocol where Bob communicates overall only b bits for some quantity b. Then we know that, in fact, we can prove that Alice must communicate n over 2 to the b bits, essentially. So there's something slightly non-trivial going on. So if Bob doesn't reveal all the log n bits of the index that Bob holds, then this means that Alice still has, still needs to communicate quite a few bits or quite a lot of information. So for example, what Bob could do, Bob could just send the most significant bits of the index. Then this eliminates a lot of positions in Alice's input. And in this way, you get sort of a non-trivial trade-off that follows this specific, follows this trade-off here. So both of these results we'll come back to later. They're going to be useful for us. Good. Okay. So so now these are sort of two different settings, but they're connected in the following sense. So we are going to use the communication complexity framework, in particular now the index problem that we've seen, to prove lower bounds for streaming algorithms. In other words, the connection, the immediate connection that we will exploit is this. Suppose we have a one-pass streaming algorithm, does a single pass, and it uses some space S. Then we can immediately use, Alice and Bob can immediately use such a streaming algorithm as a one-way communication protocol. Alice can just run the algorithm, send sort of the memory state onto Bob. And we see this as follows. So imagine we've got this one-pass streaming algorithm that uses space S. This is the input stream. So this x1 to xn is the input stream. Now, we could just partition the input stream, give the first half to Alice, the second half to Bob. Well, Alice can still run the streaming algorithm on that part of the input, then send the memory state on whatever the algorithm currently of the computation of the algorithm looks like, the memory state to Bob as a message, and Bob can continue the execution of the algorithm. So we can implement a streaming algorithm directly as a communication protocol, a one-way communication protocol in this setting. And this connection is not particularly complex, but what it means is the following. So maybe let's give one more detail just to be sure what is going on. So Alice runs the algorithm on X, sends the memory state to Bob, and Bob just continues the execution of the algorithm. So the consequence of all of this is, if we can prove a lower bound in this one-way communication setting that we have, and for instance, we prove that for problem P, we require space S in the communication setting, then it means that every streaming algorithm for the same problem also needs space at least S. Again, why is it the case? It is the case because a streaming algorithm gives us a communication protocol, and the space of the algorithm becomes the message size in this setting. So we have this connection here. So ultimately what it means is, to prove space lower bound for streaming algorithms, we have to prove lower bounds on the communication in this one-way communication setting that we see here. Okay, so here's an example. Let's prove a lower bound for streaming algorithms for computing a maximum matching. So suppose we have an input stream of edges, we do a single pass through the data, and the end goal in the end is we want to output the largest possible matching. No approximation, but actually the largest possible matching. So we're going to look, well, we said we have to prove a lower bound in the one-way two-party setting. So let's look at a setting where Alice, well, holds the graph G1 on vertex set V with edge set E1. Bob has the same vertex set, but edge set E2, and these two edge sets E1 and E2 together make up a graph. And the goal for Bob is to output the largest possible matching in the graph where we have the union of E1 and E2. If we prove a lower bound here, again by this connection, since a streaming algorithm with space S gives us a protocol with message size S, we see that if we prove a lower bound here on the message size, this translates into a lower bound for streaming algorithms. And this is exactly what we're going to do now. Okay, so the way we prove such a lower bound here will be directly by a reduction to the index problem that you've seen before. So let's see how this works. So to keep track of what we need to do, we do the following. So suppose we have a communication protocol for matching. So that is a one-way communication protocol that produces in the end a maximum matching. Now we will see that we can use this protocol to design a different protocol that now solves the index problem. And the communication complexity of these two are going to be related. So again, given a protocol for matching, we want to use it to solve index. So, okay, we want to solve index. So let's look at an index instance. Remember index, in index, alles holds a bit string. Here, the length is parameterized as n²/16. This makes sense in a minute why we go for such a length. Bob holds this index j, and we need to identify sort of the bit at position j in x. And we can do that now using the protocol for matching. And this works as follows. So based on the bit string that Alice holds, Alice is going to design a graph. And the way this graph is designed is, well, we have these 4 vertex groups. But now here on the inside, this looks like a complete bipartite graph. But what we do is, what Alice is doing is, well, Alice is going to map basically each of these bits of this bit string to one potential edge of this complete bipartite graph. So if we have n/4 vertices here, n/4 vertices here, here as well, and here as well, then the number of edges here would be n²/16. This maps exactly to the sort of length of this bit string. So Alice sees these as potential edges, includes an edge into this graph if the relevant bit is 1. If a different relevant bit is 0, then this edge would not be included. So sort of the bit string specifies exactly what the edge set in this graph would look like. Good. So in other words, Alice, based on the input to index, constructs this graph, runs an algorithm for maximum matching on that, runs the protocol for maximum matching on that, sends a message to Bob, and now Bob has this index j. Now using this index j, Bob does the following. So Bob knows the index j and knows also the edge slot here that corresponds to this index j. So Bob needs to find out whether this edge exists in the input graph. If it exists, we know the answer to index is 1. If it doesn't exist, the answer is 0. So what Bob does is Bob inserts these outside edges, these green ones. So for every vertex that's not incident to this special edge that corresponds to the edge slot, say j, Bob inserts this outside edge. And and this has now the following effect. So suppose this red edge exists, then we know that the largest possible matching are the green edges plus this red edge. On the other hand, if this edge doesn't exist, then the matching size, the maximum matching size changes by 1. It's going to be by 1 smaller. So based on the matching size that the matching algorithm outputs, one can deduce whether this edge exists or not. So yeah, the construction is basically so that this edge, the existence of this edge affects the maximum matching size by 1. Now, why do we get a lower bound here than of n² for maximum matching? Well, it's because in this reduction we've used as a parameter, sort of for this index problem, we could parameterize it by n²/16, so this translates to get a lower bound of n². Well, in other words, maximum matching in a single pass is just hard. We just can't solve it basically in streaming with something in space. Good. Is there any question about this so far?
I'm confused, sorry.
Sure.
So Alice constructs that graph.
Yeah.
But does Bob know which vertices are which set?
Yeah, good. Alice and Bob, they agree on these vertices beforehand.
Okay,
they can, yeah, absolutely. Yeah, that's a good point. Okay. Yeah, so now let's move on to really what the state of the art results on matchings are, and we see how this fits into the picture. So yeah, so let's first look at this one-pass streaming setting. So in the one-pass streaming setting, we've already seen that there is the greedy algorithm that gives us a 1/2 approximation. And it turns out that this, quite strangely perhaps, is still the best algorithm we have for one-pass streaming matching. So it has an approximation factor of 1/2, uses space n log n. This question is really very open in a very strong sense. Even if we gave you space, say n to the 1.99, then we still couldn't improve on this approximation factor of 1/2. So this is a very hard problem that has been open since a long time. So really is the best one-pass algorithm we have, but on the lower bounds front, we know a little bit more. So we know that if for these algorithms that use space n polylog n space, we know that we cannot have an algorithm that's better than a 0.59 approximation. That's sort of the currently best lower bound. The first lower bound that ruled out approximation factors better than 2/3 is now already 13 years old. We'll look into this in a minute, how this lower bound is proved for approximation factors. Good. Now, for 2 passes, quite interestingly, the answer, the barrier where we're currently stuck is 2 minus root 2 as an approximation factor, both for bipartite and general graphs. Yeah, I'm not sure why we're stuck here or why things are not moving forward beyond 2 minus root 2 in the 2-pass setting. There's no immediate reason why it should be the right answer. There are some lower bounds known, and I will talk about this in a minute. But then the other question we could ask is not fix the number of passes, what's the best approximation factor we can get, but rather we would like to have a 1 minus epsilon approximation. Well, the question is, how many passes do we need? For bipartite graphs, we know it's doable in 1/epsilon square or in 1/epsilon log n passes. And for general graphs, we also know by now that a polynomial number of passes in 1/epsilon is sufficient. So this is sort of the state of the art here. But yeah, so this connection between streaming and communication complexity is really about lower bounds. So on the next slide, I want to talk about the lower bounds that we know about approximations for maximum matching. So there's things haven't moved for quite a long time, but they're moving now a little bit faster. So for a very long time, we didn't have many lower bounds here. So the first lower bound was actually for maximum matching, not even for approximations, but for exact maximum matching in multiple passes. So we've seen in 1 pass we need space n squared, but we might now ask what happens in 2 passes or in p passes. And it turns out that the first lower bound was to say if you want the exact maximum matching, then the space, yeah, I'm not sure this works anymore. Sort of. The space is, in any case, is n to the 1 plus 1/p, so it becomes less space the more passes we have here in this setting. So this was the first result that came out. And then for a long time, nothing really happened. And then 7 years later, we have the first lower bound that said, if you want a maximum matching in 2 passes, then it doesn't degrade as 1 plus 1/2 or 1/p. We require basically still space n squared. So even if you have 2 passes, maximum matching doesn't become significantly easier. This moved on to another result that basically showed that even if we have up to square root of log n passes, you still need basically space n squared. So maximum matching is just hard, the exact version of the problem. We then had the first conditional result for approximate matching. So what happens now if we don't require the exact solution, but we're happy with 1 minus epsilon approximation? Then it turns out, well, the first paper basically proved that there exists such a small constant epsilon, which is indeed a constant under some conditioned on some conjecture, which I'm not going to go into really very much now, but it basically said, yeah, we can't get a 1 minus epsilon approximation using only this n polylog n space. Our result, and I want to talk about this a little bit, is the following. We proved that for this 2-pass setting, so indeed, if we want a better than 8/9 approximation, then this requires more than this semi-streaming space. So this is fairly recent and provides a proper constant at 8/9, and it removes all these conditional results. And I want to talk a little bit about how this result is obtained. Good. Okay, so these results in general, they rely on objects from combinatorics on Rusa-Semeredi graphs, and I want to introduce those a little bit. So So here's a definition. So suppose we have a bipartite graph, then we say that this graph is a Russo-Samaretti graph parameterized by R and T. If the following can be done with this graph, so the edge set can be partitioned into induced matchings and overall T of them. And each induced matching must be of size R. So what's an induced matching and what does this look like? So here is an illustration of this. So we have a bipartite graph here. And suppose this is one of these matchings Mi in this decomposition. Then an induced matching is one that has the property that in the input graph, basically an edge like this red one doesn't exist. And what I mean by that is, if I look at all the edges that go from the sort of left endpoints of this matching to the right endpoints, then all of these edges are just the matching edges. There can't be any other edges in the graph as well. So as an example here, we have a Russo-Samaretti graph. So let's see what the parameters would be. So the matching size would be 2 here. So we have 1, 2, 3, 4 matchings. So this would be a 2, 4 Russo-Samaretti graph as an example here. And yeah, so the question is with these Russo-Samaretti graphs, what can we actually construct? For which parameters can we come up with these Russo-Samaretti graphs? So the most useful construction for us is basically this one that I've put here on the board. So this is the state of the art, what we can construct in terms of Russo-Samaretti graphs. So what we can do is we can obtain Russo-Samaretti graphs whose matchings are basically of linear size, of size 1/2 minus epsilon n, or close to 1/2 n. And we can pack overall basically n to the 1 over log log n such matchings into the graph. So just to recap what 1 over log log n to the 1 over log log n is. So n to the 1 over log log n is between a polylog and between a polynomial. So it's not quite a polynomial, but it's also strictly more than a polylog. So these graphs have n to the 1 plus 1 over log log n edges, which is more than the semi-string bound log n that we're typically interested in. So they're kind of dense, but not really dense. They have less than n to the 1.01 edges, for example. Good. Now, for us, this density will be important of Russo-Samaretti graphs. So we might ask the question, if we want these matchings to be of linear size in Russo-Samaretti graphs, so how many can we pack into a Russo-Samaretti graph? Now, I mentioned this is sort of the best construction we have with n to the 1 over log log n matchings, but then the best lower bound that is known of how far can we push this is actually only n to the log star n. So there's a massive gap between these upper and lower bounds.
Sorry, this is a stupid question maybe.
Sure.
But this Russo-Samaretti graph, this is a maximum construction, right? Because you can look at a 2, 4, and you can think of it as like 1, 8. So how do you uniquely?
Yeah, you're right. So in this definition here, I just said I ask for linear size. So if you apply your trick to sort of partition these matchings, you can only partition each matching a constant number of times to keep it at a linear size. So it doesn't change really the.
But is there any like formalizing on how to like a maximal kind of definition of Russo-Samaretti or a given a graph, or is it?
I'm sure we could come up with one. I'm just not sure we would need it for at least for these purposes. Yeah. Yeah, it's a good point. Okay, so we have one of these constructions of these Russo-Samaretti graphs, and we're going to use that. So the first way we're going to use it is to recap on this 2012 result that basically ruled out 1-pass streaming algorithms for maximum matching with approximation factor better than 2/3. So how can we do that? So imagine Alice as input in our communication setting holds such a Russo-Samaretti graph as described before, but we do the following to this graph. We delete every edge of this graph with a probability, a small constant, very small constant. So we've turned this graph basically into an input distribution now. Every edge is deleted with a small probability here. Good, that's it. That's what Alice holds. Alice sends a message to Bob based on this graph. And now Bob holds the following. Basically, Bob holds this outside matching that I've put in here. So what is this outside matching? Well, remember the Russo-Samaretti graph has a certain number of matchings. Let's pick one of these matchings uniformly at random, MJ. And Bob will add these outside edges so that sort of every vertex that's not matched in this matching mj will be assigned a new vertex outside, and we have this sort of edges towards the outside. Now, if we see this construction, so what is the largest matching in this graph? Well, the largest matching is the green edges plus the red edges of this special induced matching mj. Good. Now, this construction has the interesting property that, well, what happens if the algorithm or Bob doesn't receive sufficient information from Alice about this special matching, about this red matching here? Well, the problem is Bob can't construct really a large matching without these red edges. This matching is an induced matching. That means we don't have any other edges that sort of go from the left to the right in this top part here. So these edges are really crucial for computing, for deciding or coming up with a big, large matching. And this is essentially the idea here. So if the message from Alice to Bob is significantly smaller than the size of this Russo-Samarelli graph, then for this, on average, for each of these induced matchings, we have only little of n bits to describe what, within this message, which means that Bob will only learn about a random induced matching, basically little of n edges. And little of n edges are just not enough to increase the size of this matching significantly. So the best Bob can do is basically pick these outside edges and whatever information in the message is about this special matching. And there's just not enough information. This gives a two-thirds approximation to amount. So this is the idea. So these Russo-Samarelli graphs, they're really very important for streaming and for proving these lower bounds. Good. Now, we pushed this construction a little bit further because we wanted to get lower bounds for two algorithms that can do two passes over the input data. And the setting, the communication setting that we have to consider now is a little bit more complex. So we will consider a one-way communication setting now with three parties involved, Alice, Bob, and Charlie. And overall, we will have two rounds. So this is Alice will send a first message to Bob. Bob sends another message to Charlie. Charlie communicates back basically to Alice. Alice sends another one to Bob. It goes to Charlie, and then Charlie outputs the result. So this communication setting covers basically the two-round streaming setting, if you do two passes in the streaming setting. So we will prove a lower bound in this more complicated communication setting here. So what's our idea? So the idea is the following. So we have Alice, Bob, Charlie. Imagine Alice and Bob now hold a large number, n, capital N, of these one-pass hard instances that we've just seen. So in other words, imagine Alice holds like a overall n of these Russo-Samarelli graphs. For now, think about them as completely disjoint, and Bob holds basically n of these indices. Now, on top of that, imagine we have another party, Charlie, and Charlie now basically selects a subset of these n instances, of these couple n instances. And in our game, suppose we say that the subset that Charlie picks, these are the instances that Alice and Bob need to solve. Then, well, this problem seems quite hard really, because if Alice and Bob have a huge number of instances, but they don't really know what to focus on because Charlie dictates which instances have to be solved, then without the information that Charlie provides, Alice and Bob can't really do that much. This is exactly sort of our idea. If in the first round, without seeing Charlie's information, whatever Alice sends to Bob and Bob forwards to Charlie, which in turn might come back to Alice, can't be that useful because we just don't know which instances need to be solved overall. And once then Charlie reveals which instances need to be solved, well, then in the second round, Alice and Bob can focus on solving these instances because now we know which ones need to be solved. So this is sort of the key idea to get from one round to two rounds. But this is, so what's the challenge? The challenge is basically, well, we can't just have these disjoint copies of these one-round instances because this would create a huge graph and then, yeah, we wouldn't get any hardness there. It uses too many vertices. So the challenge really is to pack a lot of these instances into a single graph that reuses basically vertices as much as possible, because otherwise the complexity in terms of the number of vertices wouldn't go up. So the way we do it, and I think a picture says more than this description here, we essentially come up with a hierarchical construction of these Russo-Samarelli graphs. We pick a fixed global Russo-Samarelli graph and a local Russo-Samarelli graph. Now here's our global view. The global view really looks exactly like the one-pass hard instance. So we have a Russo-Samarelli graph here. Here's a special induced matching that will be picked. And we have these outside edges here as well, similar to the one-round instance. But now what is really going on is that what we do is that every single edge of this global Russo-Samarelli graph is now replaced entirely with another local instance of this one-pass lower bounds. In other words, from this global structure, pick any edge, then this edge, for example, would be replaced by an entire local instance of the one-pass lower bound. So this means like there would be, first of all, the vertex, one vertex gets blown up into these vertex groups. We have the Russo-Samarelli graph between here and here. And if you remember, Bob held these outside edges, these green outside edges as well. So this is sort of a way to blow up a Russo-Samarelli graph into, embed another hierarchy of that into this graph. So this is sort of the graph construction that we have. Now, why is this interesting? So the interesting thing is that, first of all, these outside edges are being held by Charlie. So Charlie basically has the blue edges, which immediately means that the only instances that need to be solved between Alice and Bob are those that correspond to this induced matching here. So these are basically, this is a way for Charlie to select these important instances that need to be solved. And this is basically, these are the instances, the one-pass instances that need to be solved in the second round. Now it's even possible to see why this gives an 8/9 approximation lower bound. Basically, this is at scale, in fact, this picture here. So here on the blue side, you can see we can solve the problem optimally. So we get 3 out of 3 in some sense. Here we also get 3 out of 3 because we're optimal. But for each of these instances up here, there's only one part. Basically, from the lower bound, we get a 2 out of 3 approximation. So 3 out of 3 plus 3 out of 3 plus 2 out of 3 gives 8 out of 9 that we will get in the end. So this is just an intuition why this lower bound gives an 8/9 hardness in the end. So this is what we get. Okay. Yeah, so now just one comment why, so without going into details, how this is, ultimately the work that went into the lower bound, there's just one result that we mentioned earlier that we leveraged. And this is, remember for index, we said that if you have arbitrary communication between Alice and Bob, and if Bob only communicates few b bits, then Alice must still communicate quite a lot of bits, n/2 to the b bits. Now, in our setting, in our lower bound, remember Alice and Bob have all these disjoint Russo-Samarelli graphs. Charlie holds this certain subset. In the first round, since Bob doesn't know which sort of indices are important, essentially what it means is that Bob sends only, in fact, little o of 1 bits, or only o of 1 bits for each of these indices to Charlie, which in turn goes to Alice. So this means in the next round, Alice still has to send a lot of information, basically forward to the next party. That's sort of the rough idea of this now. Okay, good. So now I don't want to spend much time on this, but so this is sort of the picture we have for matchings. I just want to give a one slide overview about a related problem because it has an interesting message for matchings. So it's a maximal independent set problem. Basically, find a subset of vertices that are non-adjacent in a graph, and it has to be maximal, this subset of vertices. So there's an interesting state in the streaming setting. So we know that doing something exactly similar to what we've done for matchings, it's possible to prove in a single pass. We just can't compute a maximal independent set. It requires space n squared. Now, we know that there are very good algorithms that run only in log n passes, but use this n log n and polylog n space for computing a maximal independent set. And very recently, we proved that this is actually best possible. So we proved that if we have the space n polylog n space, then we need indeed log n passes to compute a maximum independent set. So this is essentially a lower bound for multipass algorithms that shows that log n passes are necessary. The reason I bring this up is because if we combine essentially this work here down here, this log